All right, let's dive right in. We're going to be talking about the invisible magic that basically makes our modern wireless world tick. It's called OFDMA, and it is the absolute core of 4G and 5G. Today, we're going to pull back the curtain and see exactly how it works.
So, picture this. You're in a packed stadium, thousands of people all on their phones at the same time. How on earth does your phone get a perfect buffer-free video stream in the middle of all that chaos? Well, the answer isn't magic. It's about solving some really tricky physics problems. And that's exactly what OFDMA was designed for.
So, before we can appreciate the solution, we really have to understand the problem. Think of the air all around us as a highway for radio signals. But, it's not some clear, open road. Nope, it's a total mess, a chaotic, unpredictable traffic jam.
See, when a cell tower sends a signal, it doesn't just zip in a straight line to your phone. It bounces off everything. Buildings, cars, trees, you name it. This is what we call multipath propagation. And what it means is your phone isn't getting one clean signal. It's getting dozens of echoes of the same signal, all showing up at slightly different times. This creates a huge headache called delay spread. Because those copies of the signal arrive late, the end of one chunk of data, we call it a symbol, starts to bleed into the beginning of the next one. This is intersymbol interference, or ISI. It's kind of like trying to read a sentence where all the words are smeared together into a garbled mess. The data just becomes unreadable. But wait, it gets worse. These bouncing signals don't just arrive late, they also crash into each other. At some frequencies, they might add up and get stronger, which is fine. But at other frequencies, they can completely cancel each other out. This creates these deep dips in the signal, where big chunks of your data can literally vanish into thin air. Gone. So, just to recap, we've got signals smearing together and other parts of the signal just disappearing completely. It's a disaster. This is where OFDMA comes in. It's the hero of our story, with a solution to this wireless traffic jam that is just brilliantly elegant. The whole idea boils down to two words: divide and conquer. Instead of trying to blast all your data down one giant, high-speed, chaotic highway where it's super vulnerable, OFDMA does something genius. It splits that one big highway into hundreds, sometimes thousands of tiny, slow-moving, and perfectly orderly little lanes. We call these subcarriers. And the scale here is just wild. For example, a standard 10 MHz 4G LTE channel gets split into 600 of these independent subcarriers. Each one is its own little private data lane. And because they're so narrow, they're small enough to dodge those deep fading dips we talked about. So even if a few lanes get blocked, all the rest of the traffic just keeps on flowing. But you might be wondering, how do you pack 600 lanes that close together without causing a massive pileup? Well, the secret is a bit of mathematical beauty called orthogonality. It's all about perfect spacing. The subcarriers are arranged so that the peak of one wave lines up exactly with the 0 point, the null, of all its neighbors. It's this incredibly clever trick that makes them basically invisible to each other. It's like they're all in the same space, but in a way that lets them completely ignore one another. Now, trying to build hundreds of physical radios and sync them up perfectly would be, well, pretty much impossible. Not to mention ridiculously expensive. So how is this actually done? Well, the answer isn't in the hardware. It's pure digital magic, powered by some really clever algorithms. So at the cell tower, it all starts with an algorithm called the inverse Fast Fourier Transform, or IFFT. First, all the data gets loaded into these digital bins, and each bin represents one of our subcarrier lanes. Then, the IFFT algorithm takes this whole map of frequencies and, in one go, transforms it into a single complex waveform. This one waveform digitally contains all 600 subcarriers perfectly combined. As a final step, a little buffer called a cyclic prefix is tacked on. Think of it like a guardrail to protect against that signal smearing, that ISI we were worried about.
Then, your phone just does the exact same thing, but in reverse. It gets that single waveform, and the first thing it does is strip off that cyclic prefix guardrail. Then, it runs the Fast Fourier Transform, or FFT, which, you guessed it, is the inverse of the IFT. This algorithm beautifully unpacks that combined waveform, separating everything back into the original 600 digital bins. And just like that, your phone can read the data from each individual lane.
Okay, so OFDMA is this incredible solution for data coming down to your phone from the tower. But here's the twist. When your phone needs to send data back up to the tower, OFDMA has a huge flaw. A fatal flaw, really. one that would absolutely murder your battery life. The problem has a name: peak to average power ratio, or PAPR. See, because an OFDMA signal is just the sum of hundreds of different waves, every once in a while, just by random chance, they can all line up and peak at the exact same time. This creates these massive, sudden spikes in the power level, and to transmit those huge spikes cleanly, your phone would need a really powerful and really inefficient amplifier. It would be a total disaster for your battery. And you can see the difference so clearly here. On the left, that's the high PAPR of OFDMA. It's spiky, it's unpredictable, and it needs a gas-guzzling power amplifier. But on the right, that's what you want for a phone, a low PAPR signal. It's smooth, it's steady, and it lets you use a much more efficient, battery-friendly amplifier. So the solution for sending data up from your phone is a clever twist called SC-FDMA, or Single Carrier FDMA. It just adds one extra step right at the very beginning. Before mapping the data into the bins, it runs an algorithm called a discrete Fourier Transform, or DFT. You can think of it like a blender that spreads the data symbols out across each other. This one little pre-coding step is all it takes. It dramatically lowers the PAPR and creates that smooth, battery-friendly signal before it goes through the rest of the normal IFFT process.
So, we've talked about the problem, the brilliant divide-and-conquer solution, the digital magic that makes it happen, and the fix for your phone's battery. Now let's put it all together. Let's follow a little piece of data on its incredible, high-speed journey from the cell tower's brain all the way to your phone.
Okay, it all starts deep inside the base station. First, your data gets some error protection added. Then it gets modulated, which is just grouping bits into more complex symbols. Next, this hyper-fast traffic cop called the scheduler assigns your data to a specific block of subcarriers just for you. Then comes the digital magic. The IFFT combines it all into one waveform and adds that cyclic prefix guardrail. From there, the digital signal has to become an analog radio wave. It's converted and then moved up to the right frequency, let's say 1.8 gigahertz. And finally, the last crucial step. A high-power amplifier takes that tiny signal, just milliwatts of power, and boosts it up to a whopping 40 watts before the antenna sends it flying through the air.
And that whole trip, from complex algorithms to a massive power boost, happens over and over again in a tiny fraction of a second, all to get you that perfect video stream while you're sitting in a crowded stadium. Pretty amazing, right? When you boil it all down, OFDMA was revolutionary because it was a way to take the physical chaos of the airwaves and impose a kind of beautiful digital order on it. It truly is the foundation of our connected world. Which leaves us with a pretty big question to think about. As we start looking towards 6G and whatever comes next, what's going to be the next huge physics challenge that engineers will have to conquer?